All right, so let's remind ourselves of some things that we did way back in chapter 8 when we were doing the slope and the intercept. We did a line of best fit. Okay, so we had this is a question straight out of chapter 8. The scatter plot below shows the number of passengers departing from Oakland, California airport month by month since the start of 1997. Time is shown as years since 1990, with fractional years used to represent each month. Thus, June of 1997 is 7.5, halfway through the seventh year of after 1990, et cetera, et cetera, et cetera. And they give us all this information. So we've got a picture of the scatter plot. We've got the line of best fit drawn on here. They tell us what r squared is equal to. Notice they don't tell us what r is equal to, and we're going to talk about that in just a second. They tell us s is this, and you're like, well, what is s? Well, we'll talk about that also, but you should know. And you don't need a calculator for this at all. There's nothing to do. It's giving you all the summary stuff here. So it says interpret the slope and the intercept of the model. So the slope is here. So notice it says the coefficient on the year, and the intercept is here. Notice it usually says that's the constant. And if you think about it, that makes sense. It's y equals mx plus b is the basic slope intercept form. So what does this tell us? Well, that the model predicts that in 1990, the number of passengers departing from Oakland was about 282,584, and this number increases at about 59,704 each year. All right, what does r squared say about the model? Do you guys remember that?
That is how it's how strong the correlation is, or something along those lines.
Well, r is the correlation coefficient.
Right.
And while we're talking about that, if they gave us r squared here, can we find r?
Yes.
Yeah, and is it the positive square root or the negative square root?
Positive.
It's a positive square root. Why?
Because.
Because,
Oh, because it's going to go up?
yeah, as we move um, from left to right, we're going up. So that means that r has to be positive. This is a positive association. So r would be the square root of 71.1. So, but back to the original question, what does r squared tell us?
It was like the majority of the data, right? Or something. It was like.
I'll just tell you this one. So 71.7% of the variation
Oh, I remember these.
in the number of passengers is accounted for by the number of years since 1990.
And how do we know which one comes first? The years since
What's the
1990?
output?
The output? Passengers? So that comes first. Okay. Oh, and it tells you right there. Deep in variable passengers.
Yeah.
Okay.
All right, and let's interpret S sub B. Sometimes they'll just write S, sometimes they'll write S sub B on these. So that's this. And what it means is that errors in predictions based on this model have a standard deviation of 104,330.
A lot.
Yeah, that's pretty big, especially when you consider that the slope is about 60,000. Right? So that means that we have years where, where we went down. Right? So this is kind of all over the place, which is why only 71% of the variation in the passengers can be predicted by how many years it is.
So that's low. Or
It's one of those ones where it's like, it's not terrible, but it's not great either. There is definitely a positive association here, but it's not strictly positive.
so the standard deviation is greater than the actual slope.
Yeah,
I was wondering.
yeah. All right, so in this problem, we had information about every month from 1997 to 2007 or so. What if we only had a sample of these data values? We could still make a regression line, but how good would it be? So what we're doing now is we're switching from, instead of having all of the data, we're just going to have a sample of the data. Right? And then we're going to make an inference. So in order to make inferences about the slope of a regression model, we have to check the following conditions. So first of all, the true relationship between X and Y must be, and it says linear here, I would say, basically linear. It's not perfectly linear, but the relationship's got to be a linear relationship. The standard deviation of Y does not vary with X. What does that mean? Well, it means it doesn't either fan out or, move in when you're looking at the residuals, or you're looking at the data. If you look at this data, our prediction doesn't get suddenly worse as we move from left to right, or get a lot better as we move from left to right. Notice you can check both 1 and 2 by looking at a plot of the residuals. remember that a residual plot should have no pattern to it. So that's actually, both of these together, you could check it by looking at a plot of the residuals. All right, the selected data points should be independent. That is, the sample should be randomly selected or from a randomized experiment, or, and this is the one you can always fall back on, you're like, it seems like this should be representative of the entire population. When sampling without replacement, the sample should be less than 10% of the population. That's one that we've done over and over again. That's to ensure independence. For a particular value of X, the responses, that is the Y values, should be normally distributed. So if the distribution is skewed, we need to have more than 30. In fact, if you have more than 30, you don't have to do anything else. All right, and this is all really familiar to you, right? If n is less than 30, the distribution must be free from outliers and strong skewness. Again, same thing we've done a couple of times. Once these conditions have been met, we're going to use the same formulas that we've been using. The standardized test statistic, whether it's chi-square or whether it's students t, whether it's z or whatever, is the statistic minus the parameter over the standard error of the statistic. And, moving on to the next page, the confidence interval is equal to the statistic plus or minus the critical value times the standard error of the statistic. So now we need to know which distribution we're going to use. It turns out that, are we going to use z? Are we going to use t? Are we going to use chi-squared? So let's start with the standard error of the statistic. There are three factors that influence this for the slope of the regression line from our sample. If we were to sample over and over from the two underlying populations that these samples come from and compute all the slopes, which groups of slopes would vary less? What measurement is different about these graphs? So of these two, one or two, I feel like your ophthalmologist. Does it look better at one or two? Two or three? Which one would have less variability?
One.
Yeah, the first one. What measurement is different about those? So the first has smaller residuals. Than the second.
Oh, these are the residual plots, or?
No, this is not a residual plot.
Oh.
These are a scatter plot.
What do you mean by smaller residuals in the second?
The residual is the distance from your,
Oh.
right? You have your regression line. So your regression line here would be like this. Your regression line here would be like this. There's bigger residuals in this second one. What about this one?
The second.
Yeah, the second one. Why?
It's more linear. Is that correct? Go that way.
Well, it's just not linear like this.
No.
It's a gap. There's gaps in the data. You can't have that. You can't have nothing and then have everything. And nothing again.
Yeah, what I would say is just that this has a bigger spread in the x variables than this does. Here all your x's are crammed up close to one another. So there's a larger spread in x. And what about this last one?
The second.
Yep. Why? Yeah, that's exactly it. It has more data points. So it turns out that the standard error for the slope b of a regression line is given by this formula. S sub b is equal to s over s sub x times the square root of n minus 1. I don't remember if that one's on your formula sheet or not. Why, yes. Yes, it is, in exactly that format. Now, notice then S is, this is the standard deviation in Y. This is the standard deviation in X from X bar. So notice these are residuals, right? The difference between those. So we want that to be, so as we go, we'd like this S to be as small as possible, right? And we'd like S sub x to be relatively large, and we'd like n to be relatively large to make this standard error as small as possible. So your book uses slightly different variables for these. I don't like the ones, the way it is that your book does it, but these formulas, just like these, are exactly what's on your formula sheet, okay? So you almost never have to calculate the standard error. However, you do need to know how it's calculated to be able to say things like, well, if I have a greater n, then I'm going to have a smaller standard error, right? Because the denominator would be larger, therefore the fraction is smaller. Or if I have this, the y minus y hat, that's the residual. Right?
Mm-hmm.
So I want small residuals. So I want S to be small. That's residuals. This is the standard deviation in X. I want a lot of deviation in X. I want a big spread of X. Right? I don't want it to look like this. I want a big spread of X. That will also help me keep my standard error low, and I want a lot of data points. If I have those three things are the three things that contribute to the standard error. So again, we almost never actually calculate all these things by hand, but you should know how they contribute.
So if you have really small residuals, then you're going to have a bigger standard error.
If you have really small residuals, you're going to have a small standard error.
Oh, right. So the opposite.
Well, because this is,
Dividing it by a bigger number, it'll be smaller. Right?
I think you're saying two different things. So S is calculated from the residuals.
Mm-hmm.
So small residuals means small standard error. Right? S sub x is a standard deviation in X. A big standard deviation in X, meaning you have a wide spread of X's,
Would be bigger for
is bigger in your denominator, so that's going to make your standard error smaller. And then if you have lots of data points, that's also going to make your standard error smaller.
Okay.
Now, again, there are limitations on that. If you're sampling without replacement, you want to have less than 10%.
Mhm.
Okay? All right. So when the appropriate conditions are met, the standard error statistic for the slope of the regression line is B minus beta, which follows a student's T model with n minus 2 degrees of freedom. So let's see, how much time do we have left? 15. Oh, we got enough time to do this. So let's take a look at an example. Data collected by the Gallup organization over 6 decades asked respondents the following question. If your political party nominated a generally well-qualified person for President of the United States who happened to be a woman, would you vote for that person? A sample of 16 years was taken from the population of all years during which the question was asked. A summary of the data analysis is given below, where the percentage of respondents who said yes, and that should be not is the response variable, it should be to the response variable. Oh no, I take it back. Where the percentage who said yes is the response variable, and the year is the explanatory variable, where 37 would correspond to the year 1937. So it's everything from 1900. So they give you all of this information about stuff. So
Sorry. Explanatory variable is the X, right?
the explanatory variable is I try not to think about it as X too much, but it's your input variable.
Okay.
So I've got a constant and I've got the year. I've got the standard error for both the constant and for the year. And I've got all this other stuff where you may or may not know what any of that really kind of means. Don't worry about it too much. Okay? Assuming that all the conditions for inference have been met, answer the following. First, find the standard deviation of the residuals and explain its meaning in context. All right. So the standard deviation is right here. That's S. It's 4.550. So the observed difference in percentage of respondents who said yes to the question from the model. So it's the difference from the how many said it from the model has a standard deviation of 4.55. Next it says find the standard error of the slope. So the standard error of the slope is right here. See that says standard error? Standard error of the constant would be the standard error in our intercept, right? The standard error in the year is going to be the standard error of the slope. So that's 0.07339. And what this means is that as different samples would produce different slopes, we would expect that the standard deviation among a collection of several samples would be of the slope would be 0.07339.
So this isn't ever actually finding like standard error, the slope and stuff when you're given a sample?
Generally, they give you summary data on these. So you're just interpreting from those. So a researcher looking at this summary notes that the slope of the regression line for this sample is close to 1 and wonders if there is any linear association between these variables at all. Write and test appropriate hypotheses. Okay. So our null hypothesis is going to be that beta, which is the slope, is equal to 0. If the slope is 0, that means as the years change, the percentage of people who would answer yes to the question never changes. So although it does make a line, there's no real nice relationship between those two, right? And our alternative is simply going to be that beta is not 0. Another way of saying this is, and you'll see this sometimes, and I do this primarily because you can get multiple choice questions and they may say it the other way. Or they can say that our null hypothesis is there is no association between the percentage of people who will say yes to the question and the year. And then the alternative would be there is an association. You may notice that this is worded pretty closely to the same way we did for a chi-squared test for independence. Our null was there is no association between these two variables, these two categorical variables from a single sample. And our alternative was there is an association. For this one, I'm not even going to set an alpha level because right up here, it gives us our p-value for the slope. The p-value is basically 0. So, using the student's t-model, anytime you use a student's t-model or a chi-squared model, you got to tell how many degrees of freedom it has. With this one, the degrees of freedom is always the number in your sample less 2.
Plus 2?
Less.
Oh, less.
So with 14 degrees of freedom, our t-value is 15.12. Which means that p is basically 0. And this is one of the few times, some of you have started mixing two things together. You've started saying with an alpha value this much lower than whatever with a p-value this much lower than my alpha value. If you have set an alpha value, don't say with a p-value this low. Say the p-value is less than alpha, or the p-value is greater than alpha, right? It's a standard that you have set in advance. Here, I didn't set a standard, so I'm going to say with a p-value this low, we reject the null. And find that there is an association. Between the percent of people who would say yes to the question and the year.
How'd you know it's a t-value, not a t-model, not a z-model? Did they give us that? Oh. Okay.
So for proportions, it's always z model.
Yep.
And for mean, it's majority of the time t model,
But if you have a whole lot of them, you could use a z. And so that's part of what's happening here. We've only got 15, or what was 16.
so they're
We have a pretty small sample.
so they're not going to use a z.
Yeah. If I was able to have, more than 30, I could probably just use a z model.
Oh, so that's okay. So that's the same cutoff, 30.
Yeah.
Okay.
So then it says find and interpret a 95% confidence interval for the slope of the regression line for all years. Okay. So it tells you that this is the coefficient on the year. That's your slope. Or at least that's what the model predicts the slope is. So that's 1.109, blah, 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 blah. So 1.109637 plus or minus. So now I need to find out, well, what is my critical value, my t critical value? So at that point, I need to grab my calculator. That's not what I wanted. So we're going to go to inference. Oh, no, sorry. We're going to distribution. Got to back out of whatever I had it in. I'm doing a student's t with 14 degrees of freedom. I must have been doing this problem at some point. And we want a 95% confidence interval. So I want between. So I want the probability to be 0.95. And I get my t critical is 2.1448. Multiplied times the standard error, which you can see is 0.07339.
Then you just solve it.
Okay? Yeah, and then you have your confidence interval, and we can explain it.
Wait, so whenever you have a t equals 15.1.12, you said it
When t equals what?
15.12.
Yeah.
Like, how do you know that that gives you is equal to pretty much zero? Like you said here, where is it? Like right there, it says t is 15.12, which is equal to
No.
t, which is practically
No. When t is this, my p-value is basically 0.
Bye, Mr. Davis.
Bye-bye. So if I'm using a student's t model with 14 degrees of freedom, and the t that I get out of it is 15.12,
that would
I'm going to get a really, really small p-value.
Okay, that makes sense. And then for the standard error, when we used it for the, what's it called, confidence interval?
Yep.
So we use the 0.07. Why again? Why not the other one?
Because we're using,
The statistics.
it's the statistic that we found,
Yeah.
plus or minus the critical value, times the standard error of the statistic.
Okay, and we wouldn't use a constant standard error because that just doesn't make sense, right?
Pardon?
We wouldn't use a constant standard error?
No,
Okay. And that's
because we're doing it for the slope. We're finding a range of the slope.
okay, thank you for giving us.
Terribly.
Yay! Can I fix that?
Why didn't you bow to Sammy?
What's wrong with it?
Can I do it now?
Pardon?
Can I do it now?
Not right now.